Welcome to welcome to all in this lecture. In the last lecture, we have seen the delta modulator transmitter circuit, and now in this lecture, we will cover delta modulator receiver circuit. So, in the block diagram, this is the block diagram for delta modulator receiver circuit. Here XDM is our delta modulated signal. This delta modulated signal is in the form of 1 or 0. If plus delta size is achieved, then it is 1, and if minus delta size achieved, then it denotes 0. This delta modulated signal is given to the integrator. Integrator produces the approximated uh, signal, which is denoted as XKF DMT. Then it is given to the low pass filter, and output of the low pass filter is our message signal. We know the relation between unit step and impulse function. This is the relation ut equal to integration over minus infinity to infinity delta t dt. Now the output of the integrator. Output of the integrator, already we have denoted it as x k of dmt, which is integration minus infinity to infinity xdm. This is our delta modulated signal, so xdm t dt. Now we have to put the values of xdmt. So what is xdmt? Xdmt is nothing but our sampled version of quantized error signal multiplied by impulse train. We have already discussed about these two signals in delta modulator transmitter. So here EQ and TS is taken outside, and now the limit of minus infinity to t summation over n equal to minus infinity to infinity del t minus nts dt. So this is our this is our output of integrator circuit, and this signal is in the form of staircase. We got staircase output. Now this diagram represents the staircase output, integrators output, and output of low pass filter, that is our message signal. So this staircase output is produced by integrator, and when this integrator's output is passed through low pass filter, then we get our original message signal, that is xt. Now the drawbacks of delta modulator. So there are two drawbacks in delta modulation. One is slope overload distortion, and another one is granular noise. So when slope overload distortion occurs, if input is fast varying signal, then it generates the problem of slope overload distortion. So this problem can be avoided by choosing larger step size, but larger step size creates another error called granular noise. And to reduce the granular noise, step size has to be reduced. So what is when granular noise is produced? When if input is slow varying signal, then it creates granular noise. So the delta modulator has two major drawbacks. One is slope overload distortion and another one is granular noise problem. So when these types of problem when a slope overload distortion occurs, then we can see our approximated signal is unable to follow the slope of message signal. uh, this is a slope overload problem, and this graph represents the granular noise problem. In this graph, our message signal is slow varying signal, and our approximated signal hunts over above and below the signal. So these both problems can be solved using adaptive delta modulation. So next technique is adaptive delta modulation. In short, we call it as ADM. Uh, Most of the part in adaptive delta modulator is similar to delta modulator, except here one block is added. This block is step size logic control block. This block gives the input to 1 bit quantizer, or we can say this blocks decides the step size. Step size is adaptive step size. It means when the slope overload distortion occurs, the step size is increased, and when the granular noise problem occurs, the step size should be decreased. So both the problems can be overcome using adaptive delta modulation. Uh, we will see how the step size increased or decreased in adaptive delta modulation. We will see using this graph. This is our uh, message signal. We can see that in this portion and in this portion, the message signal slope the message signal slopes are flat, but in this portion, this is very fast changing very fast changing signal. So when granular noise, how can we detect that this is granular noise and this is slope overload noise? So when plus delta minus delta plus delta minus delta, this type of pattern occurs, then it is granular noise. And when plus delta plus delta plus delta or minus delta minus delta minus delta, this type of pattern occurs, then it is called slope overload problem. Both problems uh, are combinedly due to quantization noise. So to reduce granular noise, step size should be decreased, and to reduce slope overload, step size should be increased. So here is a example. uh, this is a formula to calculate the step size at sampling time, that is n. The step size delta n is given by delta. This is the formula to calculate the step size, where n is the sampling instant. In our signal, we take n equal to 0, 1, 2, 3 up to 10. This is the value of our n, that is sampling instant. So we have marked sampling instant from 0 to 10. Now for n equal to 0, it means at the sampling interval n equal to 0, n equal to 0, E naught means error signal. So E naught, if n equal to 0, at n equal to 0, the we compare our message signal and approximated signal. So in this instant, our approximated signal is less than the message signal, so the error is positive, and if error is positive, then plus 1 is given. So uh, delta 0 will be delta 0 will be delta 0. So at time instant, at time instant 0, the the step size is delta 0. It means it is delta 0. Then for n equal to 1, n equal to 1 sampling instant, even we compare our message signal with approximated signal. So here our message signal is less than the approximated signal. Message signal is less than the approximated signal, so the error even is negative, and if error even is negative, then minus 1 is transmitted. Then at that instant, the step size delta 1, we put the value of we use the formula to calculate delta n. So delta 1 is equal to delta n minus 1. Here n equal to 1, so delta 0. en en will be our present error. So present error is minus 1 plus delta 0. So delta 0, value of delta 0 we have already calculated, that is equal to delta 0. And en minus 1, en minus 1 is our previous case error. So previous case error we have already calculated plus 1, so we put plus 1. Then delta 1 becomes 0. It means there should not be any change in step size, and V remains on same step size, and it goes up to n equal to 2 sampling instant. Now again we will take for n equal to 2. So for n equal to 2, the error signal E2 will be negative. Why E2 will be negative? Because we compare our approximated signal and message signal. Our approximated signal is greater than message signal, so error will be negative, and if error will be negative, then minus 1 is transmitted. So minus 1 is transmitted. Then we calculate del 2, L2. Then again we use similar formula. So in this way del 2 will be minus delta 0. So our step size will be decreased by delta, minus delta. So here the step size is decreased, this step size is decreased. So we are here, now we are here at n equal to 3, n equal to 3. Again we calculate error signal E3. Now in this case E3, our approximated signal, we are here, our approximated signal is less than our message signal, so error will be negative. This. So if we calculate for n equal to 3, n equal to 3, n equal to 3, so again we compare uh, message signal and approximated signal. So if our approximated signal's value is less than the message signal, then the error will be positive. So E3 is positive, and if error is positive, then we transmit plus 1. Now at n equal to 3, what will be the value of step size? So we have to calculate delta 3. So again we use formula. So delta 3, it means delta 3 minus 1, that is delta 2. This is the error which we have calculated recently, plus delta 0 and minus 1 is the error of previous case. So in the previous case error was minus 1. So put the value and calculate delta 3, and delta 3 is 0. It means there is no change in step size. So we there is no change in step size for n equal to 3. So we are here. Now we calculate the step size at sampling instant 4. Okay. At sampling interval 4, n equal to 4, we calculate E4, error signal, and again we compare message signal and approximated signal at time instant 4. So at time instant 4, we are observing that our approximated signal is less than our message signal, so the error will be positive. Error will be positive, and if error will be positive, then plus 1 is transmitted. Then delta 4 means step size at time instant 4 or sampling instant 4. So by using formula we calculated delta 4, and we get the value delta 0. Delta 0, it means delta 0, it means we have to increase our step size by delta 0. This is the value of one step size, delta 0. So we have to increase delta 0. So we are here. Now at time instant 5. So in this way we have to calculate the step size for every value of n, and we got the our signal, adaptive delta modulated signal, like this signal, which is sketched by pencil, is our ADM signal, and this staircase signal, which is drawn by pen, is delta modulated signal, and this is our original signal. So by observing this diagram, we can say that our ADM signal is more closer to our original signal, and here when the uh, signal is slow varying signal, that is signal is flat. Here we can observe that from time instant 0 to 4 the signal is flat, that is very slow varying signal. So here the step size is minimum, and when the signal is fast varying signal, then the step size is uh, changes according to the slope of the uh, original signal. So both the problems, that is granular noise problem and slope overload distortion, will be minimized. Here we are observing that granular noise will is going to be decreased, and here the slope overload noise get reduced. So clearly we can say by delta modulated our delta modulated signal is far away from our original signal, but our adaptive delta modulated signal is closer to the our message signal. So this is an advantage of adaptive delta modulator over delta modulator signal. So now this is the receiver part of adaptive delta modulation. So in the receiver of adaptive delta modulator, here our adaptive delta modulator signal is given to a product modulator, and here logic for step size control uh, is given the out uh, here product modulator. One input of the product modulator is our adaptive delta modulated signal, and another input of the this product modulator is the output of logic for step size control. This step size control logic is similar to the step size logic controller which we have already used in the transmitter block of adaptive delta modulator. So the output of this product modulator is given to the integrator, and by integrator here we get approximated signal or staircase version of our message signal. Then we pass this staircase version of the signal to low pass filter, and the output of low pass filter will be our message signal, which is our demodulated signal or our original message signal. Thank you for watching this video.